All right, ladies and gentlemen, let's take a look at our Unit 2 test review on how to work through the review sheet. Question 1A says, determine the average velocity of the object. And in order to find the average velocity of a position time graph, you are going to use the slope. The slope formula is y2 minus y1 over x2 minus x1. And again, I typically like to use the first and last set of data. So my x1 is 0, my y1 is 10. And then I'm going to go all the way up to the 7 right up here. And this is going to be 7 on my x-axis. And following that over, that looks like it is at 70 on my y-axis. And this is x2, y2. So this is where we're starting. It's a positive slope, so I should end up with a positive number. So I've got 70 minus 10, and those are meters, over 7 minus 0, and those are in seconds. So 70 minus 10, you get about 60 over 7. And you're going to get approximately, when you divide 60 divided by 7, about 8.6, somewhere in that range. And again, our units are meters and seconds, meters per second. And that's your final answer for your slope. The mathematical relationship or formula that you use to describe the motion of an object will start with y equals m times x plus b. That's its base formula. So when we have a linear line, we are going to use this kind of like as our secret decoder ring. Instead of y, we put what is on the y-axis, what variable is on the y-axis. And for us, that is position, equals our slope, which is about 8.6 meters per second, times what variable is on the x-axis, and that is time, so t, plus your y-intercept. Where does the line touch over here? And that's right around 10. And this is where a lot of people mess up. They forget the meters. So 10, and then what units those are in meters. So this is your math relationship. We can use that to make a prediction at different time frames. So I'm going to write this again. Your position equals 8.6 meters per second. And again, if you got close to this because you picked a different set of data points, you're good. Just use some rounding to see if you are close to 8.6. Okay, so we have position equals your slope times your time plus 10 meters. Now they gave us a new time in the problem. So what you're going to do is plug that into where the t is, plus 10 meters. And then position equals 8.6 meters per second. And then if you'll notice, these 2 seconds will cancel, leaving us with 8.6 meters. So you're going to go 8.6 meters times 26 plus 10 meters. And that's going to be your new position. Okay, so your new position, when you're typing it into the calculator, I would go 8.6 times 26, hit equals, and then add your 10. Sometimes your calculators like to organize digits in their own way, so it's better to be safe than sorry and do small steps. Okay. A for every statement you're going to pull in your slope again. Notice we're using the slope a lot. So we have 8.6 meters per second. And in math, if you have denominator is 1 second in there. It's kind of an imaginary number there, but we have 1 second. So what you can do is say for every 1 second, the object will travel 8.6 meters. Okay. And then what does the slope of a position time graph tell us? Well, we have a position time graph here. And what did that slope tell us? It's in meters per second. It has a direction, it's positive. So that means we have a velocity. Okay. The slope of a distance time graph tells us speed. Doesn't have a direction to it, but we know how fast it's going. The difference between speed and velocity is that velocity has a direction and uses displacement and displacement is how far you are from where you started. So if you have a zero velocity, remember if you are going around a racetrack, here's your little car. If you are going around a racetrack and you stop and start at the same place, there's my cat, hello. So if you stop and start at the same place, your velocity equals zero. But you will have a speed would be 10 meters per second, for example. So you can have a speed. You could be cruising at 10 meters per second, but if you stop where you start, you are not displaced anywhere. You have not moved anywhere from zero. Therefore, if you stop where you start, your velocity is zero. Now, Johnny going from Missouri to California, we are looking for average speed. So the first thing we do is we have to write this out as a formula. So S equals D over T. So I'm going to write that S equals D over T. My distance is 1,920 miles, and the time is 32 hours. Okay, so then you're going to divide 1920, divide that by 32 hours, and I got 60 miles per hour. And always make your life nice and circle the answer for us if it's not given in a box. So the average velocity equals x over t, or displacement over time. And because he stopped where he started, my displacement is zero over my time of 32 hours. And you guys know anything zero over anything is zero. So its velocity is zero. And zero is the only weird one where you really don't need units. It's just nothing. It cancels out. So the reason why they're different is because velocity has displacement, and the displacement in this case was 0. Okay. Over here, we have described the motion of the object. So the object is traveling. This is a velocity time graph, so pay very close attention to what the graphs are about. On a velocity time graph, the object starts at a constant rate of 4 meters per second in the positive direction. Then turns around and travels in the negative direction at a rate of -3 meters per second. And they traveled that distance at 1 second. Then stops for 2 seconds. 1, 2. I could add up here that they traveled at 4 meters per second for 2 seconds. I probably should. Okay, there we go. And now it wants us to do a corresponding position versus time graph. So assuming we start at 0 and 0, we have to plot our points. So it wants us to do a position time graph. And in order to figure out position, the position is the area under the graph. So for example, right here, we're looking for this area. And the area of a rectangle is your base times your height. And in this case, we've got 2 times 4, which is 8 meters. Okay, so for these 2 seconds, it went 8 meters. So in 2 seconds, because it's 2 seconds right here, so in 2 seconds, it went up 8 meters. So I'm going to see 1, 2, see if it goes up big enough. 3, 4, 5, 6, 7, and conveniently 8. So at 2 seconds, he went up 8 meters. So I can draw my line to 0. Whoops. Easier said than done, huh? There we go. So we have a straight line from 0 up until 8. Not a beautiful line, but it gets the point across. Then this section, they go in the negative direction. And again, it's the area. And that's base times height. And we're again taking it from the line of velocity up to 0. So the area in the graph there. So our base is 1 second from 2 to 3. And then our height is 1, 2 times negative 2. So that goes down negative 2 meters. Okay? So you got negative 2 meters, which means we have to go down 2 meters in 1 second. Okay, I'm at 2 seconds. I need to go up 1 second. So that means I need to come down. I got to end up on the 3 somewhere, and I have to come down 2. So there's 1, 2. But make it on the 3 line. So there we go. So we should be at 6 meters. There we go. Nice big section here. And then it stands still for 2 more seconds. So at 3 seconds, it's going to go to 5. And you guys know that if it's not moving, there is no slope. So he's going to go straight for 2 more seconds. So you should get a graph like that. How far did he travel in the time interval from 1 to 2 seconds? So from 1 to 2 seconds, they traveled 8 meters. And our work again was base times height, which is 2 times 4, which is 8 meters. Or you can just look up at this graph and say, hey, in 2 seconds, from what, oh, I lied. That would be from 0 to 2 seconds. 0 to 2 seconds. So that's not quite right. We have to go to from 1 to 2 seconds. So read those directions closely, because if it can get me, it can get you. So in 1 to 2 seconds, your base is 1 second. 1 to 2 seconds. Your base times your height. We've got 1 second is our base times our height. 1, 2, 3, 4 is our height. That's 4 meters per second. Seconds cancel. And so our answer is 4 meters. And then you could also double check yourself from 1 to 2 seconds. So right here, they started here, they went up 1, 2, 3, 4. Okay, that's where they stopped. So you can do the math, you can look at the graphs, and both are okay. Okay, letter D, you can do this a couple of ways. The displacement is how far you are from where you started. So if you look at this graph, they started at 0 and ended at 6. So 6 minus 0, and that would be in meters, get you 6 meters displacement. You could also come up to here and use the areas that you already calculated. So we have our area of 8 minus 2. So from the velocity time graph, you have 8 minus 2, and they're both meters, also get you 6 meters. So if you're given a position time graph, you can do a position time graph, just look at what line it's at on the position side. Or if you're given a velocity time graph, find the areas of each of the surfaces here, and then add them all up. So 8 plus and negative 2 gets you 6 meters. All right, so we have a new velocity time graph. Describe the behavior of the object. So I'm going to say that that's -1, -2, -3. You might have used some slightly different numbers, but I'm going to go with -3 here. And I'm going to say 1 and 2 seconds, 3, 4, 5. To just do that here. So describe the behavior. The object traveled at a rate of, this is +3 meters per second for 1 and 2 seconds. And I can even put constant rate. Then turned around. And traveled at a rate of, let's see, this was -1. This looks like it's -2 here. -2 meters per second for 1, 2, 3 seconds. Okay, that's all we know so far. So using the velocity time graph, find the total displacement for each of those intervals. Okay, this is again where we're going to use the area. And we've got some pretty basic rectangles from 0 to 2 seconds. So that is this whole thing. That is going to be base times height. Our base is 1, 2. And our height is 1, 2, 3. And that's meters per second. Again, the seconds cancel. So 2 times 3 is 6 meters. That's how far he went. From 2 to 5 seconds, again, you're going to do your base times height. Notice even I'm writing the formulas down. I would do the same thing. So your base would be 1, 2, 3 seconds times your height of -2. 2 times 3 is a -6 because this is a -2 and they're still meters. From 0 to 5 seconds, so from beginning to end, you're going to take these two areas and add them together. So you've got 6 meters from over here plus a -6 meters from here, and that is going to make it 0. So their displacement is 0. So that means they stopped where they started and they had a velocity of 0 for that whole trip. Okay, a motion map of this object. So we know the following things. We don't know where we started. The velocity time graph doesn't tell us that, but we do know we go 6 positive and 6 negative. So in 2 seconds, this is what we do. All right, so back to some motion maps. We have our object. I'm going to start it at 0. And then I did a little quick math again at 1 second for a base times a height. I've got 1 second times 3. So I know they should go 3 meters for each second. So this is 3 meters, this is 3 meters. So I start at 0, and then my next arrow is going to start at 3 meters. This is 0 seconds. This is 1 second. And then at 6 meters, this would be 2 seconds. And then notice these are longer because it is farther from 0 and it's going faster. So longer vectors go faster. And shorter are obviously slower. And at 6 meters, because remember, we kind of went a full distance of 6 meters in the positive direction, we're going to put a dot here. You can also put one here, but that would really signify that they stopped. But they did not stop. So I chose to put my 6 meters and 2 seconds up here. Notice it's at 2 seconds where it makes the switch. This one is 3 seconds, 4 seconds, and 5 seconds. So we have 5 seconds covered here. And we know that they are back to 0. So 1, 0, 1, 2, 3, 4, 5 seconds. So that's what your motion map should look like. our displacement on the first 3 seconds. So the area for the first 3 seconds. 1 to 2 seconds, we already know is 6 meters. I'll even say 0 to 2 seconds, 6 meters, right? We know that for sure from up here. Now it wants us to go to just this little area right here, and that is -2 for your base. Yeah, 1 for your base, -2 for your height. My apologies. So we've got base times height for 2 to 3 seconds. Our base is 1 times our height of -2 is -2 meters. And then so the total is 6 meters plus -2 meters should be 4 meters of displacement. And you can even look at, for the first 3 seconds, we know they started here, they ended here. So how far did they end up going? 2 and 4 meters. All right, on the back side, given the following motion map, where positions have been recorded with 1 dot each second, draw a position time graph. Again, I start with the lines closest to the number line, and then I begin by numbering them. So 0 seconds, 1 second, 2 seconds, 3 seconds. Thank the cat. We'll try that again. That's 3 seconds, 4 seconds, 5 seconds, 6, 7, 8, 9, 10, 11. So we need a scale that goes up to 11 on our time. Okay, this is a position time graph. So I'm going to take a moment and label my graphs. Okay, so here we go. This is what I have. We have 1 to 11 seconds. 0 is here for both. And it goes 5 meters. And now we just have to plot our points. 0 seconds, it's at 5 meters. So 0 seconds, 5 meters. Put your dot up there. There is your y-intercept. Done. At 1 second, it's at 4 meters. At 1 second, it's at 4 meters. 1 second, 4 meters. At 2 seconds, it's at 3 meters. 2 seconds, 3 meters. Okay, take a moment and plot those points. All right, so this is the graph that I ended up getting. I've got, notice this solid straightforward spot is 3 seconds is at 2 meters, 4 seconds is at 2 meters, and 5 seconds is all at 2 meters. These guys went in a negative direction, then they stopped, then they went in the negative direction again, then they stopped, and then they went really fast in the positive direction. Describe the motion. So again, the object starts at 5 meters, travels at a constant negative velocity for 3 seconds, stands still for 2, stops again for 1, 2 seconds, then travels in the positive direction for 2 seconds at a fast, constant velocity. And that should get you going there. All right, now we have to do a velocity time graph. So we know that there are constant velocities. Object 1 is going faster than 2, so I put it way high up here, okay? Velocity for the object 2 is not as fast, so it goes less. If one of them happened to be negative, you'd put a line down here, okay? The starting position does not matter for a velocity time graph. If it asks you to do a position time graph, you can start it anywhere, but to make your life easier, I'd recommend starting from 0. Why not? Description, both start at 0 at a constant rate because it's a linear line. Positive direction, object 1 is faster than 2 because it's steeper, it has a steeper slope, and it ends farther from 0 than object 2, okay? To draw that as a motion map, we know that object 1 goes all the way to the end, or really close to the end. So in your description, it said go up to 4 seconds. So I've got 0, 1, 2, 3, 4. Notice they're evenly spaced. They have congruent marks to show that I meant for them to be all the same size, even though I did them from 0. And then down here, they're half the size because they went half the speed or a lot slower. And notice they did not go as far. They ended up about halfway through the end. So if you're looking for an object 2, they should be much shorter and not even close to the finish line. All right, so when I ask you to do a graph, we will be looking for, myself and Ms. Clarkston, a position time graph. You need some sort of a title. I know it says Desmos. That was more for anybody that was in quarantine or at home. So you can just doodle a regular graph. You have position in meters, so you have time in seconds down here. So you have a variable and a unit on each side. You have a proper scale on each side, and then you plotted your points with a line of best fit. Okay, and that's run us through the whole thing. So ultimately, you should be able to use the slope on a position time graph to find velocity. You should be able to figure out how far an object is from 0 by using the area under a velocity time graph. You should be able to use the equation, position is velocity or your slope times your time. If you have a position time graph, you should be able to describe the motion in words. You should be able to draw a velocity time graph, draw a motion map, and find the average velocity, aka the slope. You should be able to write a mathematical model that describes the motion, and that's the thing that starts with y equals m times x plus b. But we translate that into position equals your slope times your time plus your y-intercept. If you have a velocity time graph, you should describe the motion, draw a position time graph, find the displacement, draw a motion map, and again, write a mathematical model. So that one would be distance equals your slope times your time plus a y-intercept if there is one. And if you were really a rock star, it would be distance equals speed times time. And this guy up here would be position equals velocity times time. Okay? Make sure you're looking over any and all of your old handouts that we did together. Make sure that you can do the position and velocity time tables, and then study with your lab partners to keep reviewing. Okay, good luck. The test is tomorrow.